Hey everybody, today I'm going to talk about how to measure the length of a curved line on a plane using calculus. Alright, so here we go. Okay, so you got a circle here, alright, and let's just say that you for example, you want to split the circle right here and you want to get both ends and you straighten it out. You want to see how far that is, but yeah, if it's a circle, it's just 2 pi r, but let's just say that it's not a circle. If it's a line, for example, like this one in here, okay? Now, you want to get this end and you want to get this end, you want to straighten it out, and you want to see how long it is. So how do you do that with calculus? Well, I decided to prepare the material in advance here because I didn't want you guys to sit there just staring at me writing this stuff. So we're going to get extremely close. This is a circle, right? So we're just going to use this as a curve. And we're going to get extremely close to this part right here. So this thing here actually represents just this part. It's zoomed in. And now we're going to zoom in on just this part right here. You see that this resembles a straight line, okay? So the closer you get to a curve, the more that little piece that you're getting close to is going to resemble a straight line. Now, what is calculus about? Integration, okay? This is the symbol of the integral here. So what does that mean? Well, you guys can already see the formulas here, but I want to just say how I got to this point, okay? The reasoning behind this. So integration is about adding things that are infinite in number. You're going to have an infinite number of infinitely small things. Okay, and all these things put together are going to form the whole stuff. So when you have a curve, you have all these little bits and pieces that you're going to add together. And these little bits and pieces just resemble very much infinitely close to a straight line in their own right. So we're going to calculate the length of this. Okay, here's a straight line. Well, something that looks like a straight line that resembles extremely close to a straight line that came from this part right here of this curve here, okay? So you want to add all these things together. If you add all these pieces in here, you're going to have the whole line, okay? Now, you can integrate this with respect to x or with respect to y. Let's just do it in the case of x first, all right? So you're going to take one step to the right, and then you think, okay, how far is this step? Well, this one step is infinitely small because we're talking about integration. So it doesn't matter if it's 1 feet, 1 meter, 1 centimeter, 1 femtometer. It's infinitely small, but it's one step to the right. Okay. And now here, what are you going to have? How much does it go up? Well, it goes up dy. Okay. Why do we care? Well, because this thing right here is going to form, okay, something that looks like a right triangle. Okay. And you're just going to use the sides in here to find out the length of this little piece. And then you're going to add all the other little pieces together the same way, and you'll find the length of the curved line. So it's going to be square root of 1 squared, which is 1. It's right here. Okay. And then you're going to add this thing in here. But what is dy? Well, in this case, dy is going to be equal to dy dx. Because x is 1. So dy is just dy dx. So what do? You say 1 squared plus the square root of dy dx. It's very important that you got to remember that this is the square root of the first derivative. It's not the second derivative. Okay, it's a difference between the second derivative of dy of y with respect to x and the first derivative of y with respect to x squared. So we're going to have dy dx squared. And you just multiply that. Well, it's a multiplication, but it's also the variable of integration with respect to dx. Now in mathematics, you have something called symmetry. So if you want to integrate with respect to y, instead of taking small slices of x like this, let's just say that you want to take slices of y like this, okay? If you want to do that, you use this formula right here, which is square root of 1 plus dx dy squared with respect to dy. Okay, now there's a third formula that's going to be needed. I'm just going to show this to you guys here. Okay, this is the third formula. This one right here. Now, where does this come from? Well, it comes from the fact that sometimes you have x, you have parameterized curve. So you have x with respect to a parameter that varies according to a parameter. In this case, it's theta, and you have y that varies according to a parameter that's also theta. Okay, so you have here on this side here, okay, you got x equals r cosine of theta and y equals r sine of theta. So now x and y, y might depend on x, but x depends on theta, so y indirectly depends on theta too. So these are the two formulas of the previous slide. Now, how do you transform this thing into this, okay, into something that's integrated with respect to theta? Because you're going to need this formula to find the perimeter, the circumference of a circle. So you have this original formula in here, okay? These two formulas are the same. So you have square root of 1 plus dy dx squared. Now, I'm multiplying d theta here, and I'm also dividing by d theta, because if you multiply, you got to divide, so the expression is going to be unaltered, okay? Now, I want to put this dx d theta inside the square root, but if I do that, I have to square it, and when I do, I have to multiply by everything that's already inside the square root. So you have 1 plus dy dx squared, which is here, and dx d theta is going to be brought inside the square root, multiplying everything that's inside the square root over here. Okay? So now, dx d theta squared times 1 dx d theta squared plus dx d theta squared times dy dx squared, you're going to cancel this x with this x, and what are you going to be left with? You're going to be left with dy squared, which you got here, times d theta squared, which is what you have here. And all of this with respect to theta. Now, when, for example, why am I teaching you guys this stuff? Because we're going to need this formula right here, this one right here, to find the lateral side of the lateral surface area of a cone, okay, of a right cone. We're going to calculate the surface area, and we're going to need this formula here. And this formula here is going to be used to calculate the circumference of a circle in future videos that I'm going to post to you guys. So that's it for now.